The goal of our group was to implement multi-object tracking algorithms for processing of surveillance footage. The multi-object tracking algorithms must process the frames in real time to make tracks around targets with visible trailing paths if desired. The general cases of variable lighting conditions, target re-identification, and groups splitting or converging must be addressed. The multi-object tracking algorithms were implemented using MATLAB functions that are either open source or the corresponding math is well documented such that the algorithms could be implemented in another programming language. For each input frame, first we perform background detection. Then, with the background subtracted, we perform blob detection. For each blob, we apply a mixture of Gaussians model that allows us to re-identify the track if it either leaves the field of view or the frame is dropped. We then apply a Hungarian cost assignment algorithm to the current frame that allows us to compare it to the previous frame and determine which track is which. Then a Kalman filter is applied that not only allows us to predict where the tracks will be in the future, but also smooths them out. Finally, we plot a box around each blob as well as a tail showing their path as they move across the frame.
Background detection was used as the foundation to preliminarily identify tracks. This was accomplished by using a learning period of 20 frames where every frame is sampled. After the learning frame, every 10 frames are sampled and inputted into a 20-point moving averager. This allows the background detection to adapt to changing lighting conditions in the scene. For the primary data set we considered, we had changing lighting conditions in the bottom left portion of the screen. This required us to use a dynamic background subtraction algorithm to successfully track objects that walk through this portion of the field of vision. The next step in the processing chain was blob detection. This was primarily used in the learning frames. For each of the learning frames, we defined a mask as the background minus the current frame. After we solved for the mask, we used an adaptive noise filter to filter out most of the lighting conditions. This was accomplished using a Viner 2 adaptive noise filter. It's a built-in MATLAB function. From there, we thresholded the output of the filter. One of the shortcomings of the simple blob detection was when the target walked through the lighted region of the video. The target would essentially get pierced into several fragments. If the fragments were large enough, the target would become multiple tracks, one centered around the head and maybe another centered around the leg. If the fragments were more numerous and smaller, they would not get past the area threshold, and this target would simply be lost. Our solution to this was an iterative process. We'd attempt to connect the blobs and then filter noise, and we'd keep repeating this process until we converged on a single blob for a single track. This process was relatively effective. One of the limitations, however, is that it makes it more challenging when people are walking in groups to differentiate blobs.
To obtain the mixture Gaussians model, we index the subframe, the bounding box of the track, at the points where the track was detected. From there, the XY position data and the color data are reshaped into a vector. This reshaped data is sent into the supplied EMGM function that calculates mixtures Gaussians. If the track has also been detected previously, the means of the mixture Gaussians model from the frame before are also input into the function so that the Gaussians are consistent between frames.
One of the major goals of our project was to successfully re-identify targets after they've left the screen. Before using the MOG implementation, we were using the Hungarian cost assignment matrix, which makes the best guess based off of just previous centroid data. The next step was to use color histogram data to attempt to re-identify. We did a dot product between the color histograms of the unidentified track and all the previous tracks. This value was then thresholded to make an appropriate guess. This method, however, had limited functionality, and we ran into issues, like when groups of people were walking next to each other. MOG implementation was the fix to this issue. It was similar in theory to the histogram approach, but MOG brings to the table more accuracy, since position data is taken into account. We used a Hungarian cost assignment matrix with this MOG data to once again find the best possible match. In this video, you can see how the robust MOG re-identification algorithm successfully re-identifies the target that previously left the screen. Here you can see how the MOG algorithm is strong enough that it doesn't falsely re-identify a target, even though they entered and exited in similar locations of the screen.
Another goal of our project was to predict the movement of the tracks that were already identified within the scene. To do this, we implemented a Kalman filter using a state-space model. This model predicted a constant velocity of the tracks within the scene. The Kalman filter state-space model was updated for each frame within the scene using the center of the detected track. If the object within the scene was still identifiable through blob detection, the center of the blob was used to plot the track. However, once the object left the field of view, the track was predicted using the state-space model. This model also allowed for an object to be continuously tracked even if it was blocked by a stationary object, as you can see in this video. The Kalman filter successfully predicted 95% of the location of the tracks within a 2 pixel range for both X and Y positions. This is shown here as a box plot for a video with 4 tracks. The Kalman filter data also allowed for us to plot the position data as a smooth curve in an X and Y versus time plot that is shown here. This finally allowed us to plot velocity data in pixels per second in real time for each track within a scene.
For our future work, we need to work on the issues showcased in these videos. More specifically, we are having issues with separating large groups of people. In the current form of our code, we treat the big group of close people as one person, but when they start separating apart, we successfully re-identify them as the correct targets. See here how multiple targets close together are treated as one target.